Alright, so for 9.8, it's basically telling you there's a carbon-oxygen bond in carbon monoxide, so CO, and it tells you the length. So if we kind of visualize this, we have a carbon bonded to oxygen in CO, and the distance of that bond, the length of that bond is 1.13 angstroms. Angstroms is just a way of measuring bond length, okay? And then it gives you another one, gives you another carbon-oxygen bond, but this time it's in CO2, and this one, if you look at it, is a little bit longer, right? 1.24 angstrom, so a little bit longer. Okay, and then it's basically saying, without drawing a Lewis structure, do you think CO contains a single, double, or triple bond? Okay, now, let's think about what we learned last time at the end of class. We talked about how different bonds have different lengths, right? Which one did we say is the longest bond? Single is the longest because it is the weakest bond, and triple is going to be the shortest. It's the strongest bond. Okay? So I believe we did CO2 last class, right? And if we did CO2, do you remember what the bond was? It was a double bond. And so CO2 was a double. That means this is a double bond. And if it's shorter, it means it's going to be triple. Okay, so there you go. That's how you can determine CO without even drawing the Lewis structure. If you wanted to, you could draw the Lewis structure, and you would see it's going to be a triple bond in between them. Okay? All right, so that's pretty much all you need to know for bond lengths. Just know that single is the longest, weakest bond, and triple is the shortest, strongest. Yeah, from then you would, if we didn't know CO2, then we would just know it's not a single, right? Because it has to be one of the shorter ones. And then from there, you can just kind of guesstimate based on the number of electrons. So you would know this is 6 and this is 4, so that's a total of 10, right? And so you need to have 8 for all of them, so there's probably going to be 6 in between, 2 on the ends. Yeah. A better question if we didn't draw CO2 before would be, it would give you another CO bond, and then that would be even longer, and then from there you could cross elimination. Yeah. So this question works because we did CO2, but we could refine it for if we didn't. Great question, though. All right, so let us get into, I guess, the most important concept for this unit. Learning how to draw the structures is nice and all, but this concept right here is what's going to determine how these molecules interact with one another. Okay, so we're going to be talking about something called bond polarity, and it has a lot to do with electronegativity. Okay, now if you guys remember, electronegativity is how much the electrons want to hold on to their, the elements want to hold on to their electrons, correct? So because different elements have different electronegativity, even if they're bonded and they're sharing the electrons, they're not shared equally. So let me give you an example. So let's say that we have hydrogen and it's bonded to F. Okay. Now, if you remember, which one is more electronegative? F is the most electronegative, right? So it's most. This one is more electronegative. And so even though you're sharing 2 electrons right here, the electrons are going to be with the fluorine more often than they are with the hydrogen. So they are being shared, but let's say I drew the electrons. If we had the electrons are going to spend more time closer to the fluorine, so they're going to fly around the fluorine more than they are going to fly around the hydrogen. So they might make like one path, but in that same time, they're flying all around fluorine. Okay, and the reason why is because fluorine is more electronegative. So when we have this unequal sharing, that's what we call a polar bond. Okay, polar, like Polar Express, right? But polar just means that polar bonds are where the electrons are shared unequally. One element holds on to the electrons more. And we determine that by comparing the electronegativities. Okay? Now, there are also nonpolar bonds, and nonpolar bonds are when they're shared equally with one another. So a lot of times this happens when you have a molecule where the bond, if you look at Cl2, if they're both the same element, same electronegativity, right? So this would be a nonpolar bond because the electrons are shared equally. There's no element that's stronger than the other. All right, now there is one important, very important non-polar bond you need to know, and that's going to be the bond between carbon and hydrogen. Okay, carbon and hydrogen have very similar electronegativities, and so if you see a molecule with a bunch of carbon-hydrogen bonds, more likely than not, it's going to be a non-polar molecule. So just keep that in mind. That's one to keep in mind. But we'll see a lot of examples like that. So, all right. So we're gonna look at a couple molecules, and I want you guys to see if they are polar or not. Now, before we do that, I want you to draw these three molecules. I know that for some of them, you can just look at it and you can tell if it's polar or not. But I'm gonna show you guys how to indicate polarity. So how chemists draw it. So I want you to draw these three molecules, the Lewis structures first, and then just write underneath the molecule if it's polar or non-polar. And then we'll talk about how to draw the special symbols for polarity. So take about 3 to 4 minutes to do that, and then we'll go over together. All right, so F2 is pretty simple, right? F has 7 valence. There's 2 of them, 14. So 2, 4, 6, 8, 10, 12, 14. Okay, now, if we look at this, you got the same element on both sides. So is this polar or non-polar? This is non-polar because there's no element that is more electronegative. They're the same, right? So this is going to be a non-polar bond. Hey, good morning. Thank you. All right, let's go to HCl. HCl is also pretty simple. H is 1, Cl is 7, total of 8. So 2, 4, 6, 8. If you look at this and you compare the two, which one is more electronegative? Chlorine is more electronegative. So the way that we indicate one side is more electronegative is underneath the molecule we draw an arrow, but we kind of have like a plus sign on the side that the arrow is not pointing to. So you point the arrow towards the more electronegative element, and then you put like this little line through it. So this arrow indicates polarity. So whichever way it's pointing, that side is going to be the more negative one. Again, this is going to be a polar bond. All right, we got BCl3. B is 3, Cl is 7 each. There's 3 of them, so that's 21, so 24. So if you count them up, you should get 24. All right, now for this one, let's compare the Cl and the B. Which one is more electronegative? Cl. So it's gonna be more polar towards Cl, and it'll be the same for all 3 of the bonds. Okay, I'm just gonna draw it 3 times just so we know. But in this bond, the Cl is a more polar, so this is gonna be polar. All right, I'm gonna have you guys try 9, 10, but before we do that, I do need to tell you the one more thing. Now, it's not just polar and non-polar. There are degrees to polarity. So there can be more polar bonds and less polar bonds. Okay, so there are some bonds that are more polar, some that are less polar. Now, the key to knowing it is that the greater, so the more, the greater the electronegativity difference. Okay, the difference in electronegativity between the elements, the greater that difference is, the greater the polarity. Okay, so the more electronegative one element is than another one, the more polar it's going to make that bond. Okay, so with that being said, you'll probably need to look at a periodic table for this, but I want you to try 9, 10. There are 4 different bonds. I want you to identify which one is the most polar bond. All right, so there are 4 different bonds, and you're trying to find out what the most polar bond is, right? That means you're going to look for the greatest electronegativity difference. Another way of saying that is you want the bond where the most electronegative element is bonded with the least electronegative element. That's another way to think about it. So you're just looking for which bond has the greatest difference. So you have 4 different elements that you're looking at here. So you're trying to figure out which one's the most electronegative, which one's the least. So between the 4 on this list, let's start with the most. Which one is the most electronegative?
Cl.
Yes, Cl is the most electronegative. we can use that easy pattern as you go up and to the right. It becomes more electronegative. So Cl is the most electronegative, and out of the four, which one is the least electronegative?
SE.
Se. And so your answer will be the SeCl bond, and that's the reason why. Biggest electronegativity difference is going to result in the most polar bond. Okay. If you got that, great job. You're a genius. All right. Little bit of notations. I already showed you how to do one way of drawing the polarity, but if you have a bond, there are two different ways to do it. My bad, I forgot to tell you about one way. But one of the ways you can indicate polarity is by drawing the arrow we talked about. There's another way of drawing it though, and the other way is to draw this thing. It looks, I'll kind of draw it big right here, but it's like an 8 that's incomplete. This means partial. Okay, so partial. And if you put a positive next to it, it means partial positive. And if you draw this incomplete S and a minus, that's going to be a partial negative. So what this is basically telling us is that if you have a molecule where you have a polar bond, the electrons are going to spend more time with the element that's more electronegative, right? What that's going to do is it's going to result in a polarity, which means one side of the bond is going to be more positive and one side is going to be more negative. It's kind of like an ion, but it's not actually an ion, it's just partially. So we indicate that with this symbol. This means that this side is partially negative and this side is partially positive when you're comparing it with each other. Yeah. No, because we can do that with different elements. So like if F was bonded with O, F is still more electronegative, right? And so it's going to be partially negative, partially positive. The partial negative, correct, yeah. And since we get a plus and minus sign, we get this polarity, what happens is these molecules start to rearrange themselves based on the polarity that other molecules have. So let's do 911, and we'll see an example of what that looks like. So we're going to draw HF. Let's just draw one HF. And we just said that hydrogen is partially positive and F is partially negative, right? So when we have these molecules, we never have just one of the molecules by itself, right? There's always moles of them, right? What do we say it was? Sextillion or something? 602 sextillion of them. But what happens is these molecules, they rearrange based on the polarity. So what's going to happen is another hydrogen HF molecule comes up next to this HF, and it's going to see that, hey, this side's partially negative, and this hydrogen is partially positive. And they're going to be like, oh, that's my opposite charge. That side of the molecule looks kind of cute. And then they start to form this partial connection. They have this weak attraction to one another because one side is partially negative, one side is partially positive. And then on the other side of that HF, another HF molecule is going to be there and be like, oh, this side of that molecule is kind of cute, it's partially negative, and they're also going to form a connection. Okay, so they'll rearrange themselves based on the partial polarity of the others. Okay. And what we call this, where there's an attraction but not a bond, so let's indicate this. This is going to be an attraction based on the polarity, but it's not a bond. This is what we call an intermolecular force. Okay, we're going to talk more about this later. But this is actually the title of the unit, intermolecular forces. So this whole unit is basically going to be based on these polarities and things like this. How do these molecules start interacting with each other without bonding, without actually making that commitment? A lot of times I'm going to call this IMF. So if you ever see IMF, it doesn't mean International Monetary Fund. It means intermolecular force. So just keep that in mind. On. So Do we need to talk about this right now? No, we don't. Okay, so we are going to practice drawing a little bit, and what we're gonna do now is I'm gonna show you guys another way you can look, or the way that you can look at intermolecular forces and polarity with more complicated molecules. So I want you to draw these two molecules, CH2Cl2 and HCN, and then we'll go over them, and then we're gonna look at their polarity as well. All right, so for 12, we're going to count up the electrons first. Carbon is 4, hydrogen is 1 each, so that's 2. Chlorine is 7 each, so that's 14. That's going to equal to a total of 20. Okay, so carbon always goes in the middle. Hydrogen goes on the outsides. Now you can orient this however you want, but it's going to be very simple as long as you have everything connected to carbon. And the chlorine has 6 lone pairs, you're good. So something like that. Again, if you have the elements in different positions, that's totally fine, as long as they're all connected to carbon. In terms of the polarity, it's going to point to wherever the chlorines are, because the chlorine is the most electronegative part of the molecule. So as long as your arrow is pointing towards the chlorines, you're good. You're good. Let's look at HCN now. We have 1 for the hydrogen, 4 for the chlorines, and 5 for the nitrogens. That's a total of 10. We know that carbon needs to be in the middle, and so we're going to put H and N next to it. We're going to use 4 in order to get everybody connected, and then you're going to see that you're going to need a triple bond here and a lone pair on nitrogen. That's how you get to 10. And then for the polarity, nitrogen is the most electronegative, so there's going to be a polarity towards nitrogen. All right, so some of you guys might be looking at 12, and it might be a little bit weird because depending on how you drew it, the arrow might point the opposite way. And you might be wondering, well, how do I draw the polarity if I split up the chlorines, right? So let's say we did carbon here, and the chlorines look like this, right? Because then which direction do I draw the arrow? Well, we're going to talk more about that later, but the key thing to remember is that these molecules are three-dimensional, and so what's going to happen is there's going to be a side where even if you draw it like this, it's going to be coming like out of the page right here, where the polarity is going to lie. So the polarity would actually be coming out of the page from here. But we'll talk more about that later. We're going to skip this one. All right, so we're going to be talking about a pretty annoying concept. I really don't like this concept, but it's important to talk about. And sometimes they ask you questions on it. But there are multiple ways to draw a Lewis structure while having everybody obey the octet rule. So you don't need to draw these diagrams. But here we have CO2. And if you look at these two images, they are both viable ways to draw CO2 based on what we know so far, right? If we take a look here, oxygen has 8, carbon has 8, oxygen has 8. So this is a viable structure. But if you look at this one where it's a bit uneven, you'll notice that this oxygen also has 8, carbon has 8, and oxygen has 8. So they both work under the octet rule. However, there is a better structure. There are some structures that are more accurate, some that are less accurate. And we find out what is most accurate by using this thing called formal charge. So I want you guys to I want you to write this equation. I know that it's kind of long and annoying, and I don't like doing this, but I want you to write the equation. I'll show you how to use this equation to determine what the best structure for a molecule is. God bless you. All right, so formal charge is basically a way to designate a number to an element in a molecule. So every element in a molecule is going to have its own formal charge. So this has a formal charge, this has a formal charge, and this has a formal charge. They have their own individual formal charges. And when you do a formal charge question, you get to calculate one for all 3 of the elements, which is why I don't like doing this because it's very tedious. But formal charge is how we determine which structure is the best. So let's what we're gonna do is we're gonna calculate the formal charge of each element in the molecule, and I'm gonna show you how to do that. So we use this equation right here. Now, you guys wrote down these terms, but I'm gonna give you my terms the way that I remember in my brain. So group number is basically just what box the element is in the row. So you know how we count the boxes to get the valence electrons? That's just what that group number means. So if you look at O, if you count the boxes for O, it's going to be 6, right? So for formal charge of this oxygen right here, we're going to start with the number 6. And I'll start color coding this so it's easier for you guys to see. And then it's going to be minus the number of covalent bonds. Basically, how many lines is attached to that element. So if you look at O, how many lines are attached to O in the picture? 2. So it'll be minus 2. And then lastly, the number of electrons in lone pairs, basically how many dots are next to the element. So if you look at O, there are 4 dots. So minus 4, which means our formal charge for this oxygen right here is going to be 0. Okay? Make sense? Alrighty. So what I want you to do now is I want you to take about a minute or two and find the formal charge of this, 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 and this. Okay? So find the formal charge of the remaining 5. And then after that, I will explain to you guys how to figure out which structure is best. God bless you. God bless you.
Thank you.
What?
We're singing your name, singing your praises.
No, you're not. I know y'all talk mad trash behind my back.
I've never talked trash about you in my entire life. Whenever I talk about you, Phil, I only say the nicest things.
Bull crap.
Sam can attest. I only say nice things about Paulo, especially last night.
He loves you.
What have you done for me that's nice recently?
Why are you talking about me at night, you weirdo?
Yo, that night before the Chem test, the night before Halloween was Mr. Oh, I'm not gonna lie.
See, but didn't that actually make Halloween spookier?
It did. No, because you messaged me being like, stop procrastinating, lock in.
You messaged me, you creep,
Did I?
and I replied.
Oh.
Don't
My
be
bad.
making it seem like I'm messaging minors first. And my replies were very short and curt. It was just like, sucks to suck and stuff like that.
Except if it's not infinite.
Can you use the restroom?
Yeah, of course.
Sorry.
Alright guys, I'll give you another minute and then we will go over the formal charges.
Find the example you chose bad. You should have chosen an example where the correct answer wasn't equal there.
What?
I said, where's your box?
What box?
You used to have your little box set up.
Shut up, dude.
Oh
Stop
my
talking about the box. What's in the box?
Different colors today.
Matches the sweater. Look at him. What's his name right here?
Connor.
Connor.
Do you have Connor?
I did. I love Connor.
You like Sam? You got him.
Yes, love Sam. Sam's amazing.
You don't remember this kid?
You don't remember.
I
Why
do.
are you lying?
I
Why
do.
are you lying?
But I had you 2 years ago. You've grown up a lot. There's no way I had you last year.
Yeah, you did.
No.
Yeah.
Are you a junior this year?
Yeah.
You've changed a lot, dude. You got the mustache and the little...
He has more facial hair than me.
Well, that's not really that big a deal, is it?
It's okay, I have more hair on my head than you.
Oh, burn.
All right, let's go over the formal charges, everybody. Oh, that was on video. Okay, so let's go to carbon. So carbon is going to be box 4. There are 4 lines on next to it, and there are 0 dots. So carbon has a formal charge of 0. Everybody good? And then if you look at oxygen, it's kind of the mirror image of this oxygen, so you don't even need to calculate it. It's 0. Everybody good? So this CO2, all the formal charges are 0. For this oxygen right here, we're going to start with the box number 6 minus how many covalent bonds? 1. And there are 6 dots, so it's going to be a total of -1. So you guys can see how the formal charges are different now based on the structure, right? I'll speed a little through this. This carbon right here is going to be 4 minus 4, which will be 0. And this oxygen right here will be 6 minus 3 minus 2, which will be +1. So these are the formal charges for each element. Now we need to determine what the best structure is. Now, the way to determine the best structure, the rule's right here.
There's a fly.
Where? Oh, on the projector. That's crazy. Is it still there? It looks like Godzilla on there. Alright. Come on, fly. Alright, so the dominant Lewis structure, the way to determine it is first, if possible, you want everybody to have a formal charge of 0. Okay? So the best structure is one where every element has 0, if possible. However, if it doesn't work, then you want the formal charge of the electronegative atoms, so the most electronegative ones, we want those to have the negative numbers. Okay, so we'll see a couple examples of this later, but the best structure is one where everyone is 0, but if that is impossible, we want the more electronegative atoms to have the negative formal charges. Okay. All right, so let's start with the molecule on the left. So we're going to start with the nitrogen. Nitrogen is 5. Then we're going to remove 1 for the line, so -1. And then there are 6 dots, so -6. So that's going to be a formal charge of -2. Let's go to carbon. Carbon is 4. There are 4 lines. There are no dots, so that's going to be 0. And then sulfur right over here is going to be 6 minus 3 lines minus 2 dots, so +1. All right. Everybody good with those formal charges?
Yeah.
Okay. I'll speed up a little bit. I'll still show my work just so that you have it as a reference. This nitrogen right here, be 5 minus 2 minus 4. That's going to be -1. Carbon right here will be 0 because it's going to be same thing as before, 4 minus 4 lines. And then the sulfur right here will be 6 minus 2 lines minus 4 dots. That'll be 0. Lastly, we have the nitrogen right here, 5 minus 3 minus 2. It's going to be 0. Carbon right here, this is the same thing, so I'm not even going to write it. It's going to be 0. And then the sulfur right here will be 6 minus 1 minus 6. That'll be -1. Okay, so those are your formal charges.
I want to be the one who knows my heart.
All right, so let's talk about what structure is best. Now, we can actually pick one that's worst. What do you think the worst structure is based on what we learned so far?
Right.
The first one is the worst one. Why?
Because
There's 1 0, right? The others have 2 zeros. And so this will be the worst structure. This will be bad. Okay, so we can cut that off. Now, there are 2 that have 2 zeros and a -1. And so for this one, this problem, we can't have all 0, so we got to pick the one that's the most electronegative. Now, we need to determine basically, is nitrogen more electronegative or is sulfur? Which one's more electronegative? Nitrogen is more electronegative. We want to give the electronegative ones the negative charge. So this middle one is the best structure. If you got that, great job. That's all you need to know for formal charge. All right, let's move on. Oh, more fun. Okay, so we talked about how there's formal charges where you have a best structure. What that implies is that there are multiple Lewis structures for molecules. However, that leads us to something called resonance structures. And what resonance structures are is they basically tell you when a molecule does not have just one dominant Lewis structure. Resonance structure is a way for us to describe it when, again, there's not just one Lewis structure that perfectly describes a molecule. So, for example, let's take a look at O3 ozone. Oh, what just happened? O3 ozone right here. There are two different ways to draw it. Now, I'm going to call this oxygen 1, 2, and 3. And this one's going to be 1, 2, and 3. Now, if you look at these two different structures, you guys see how there is a double bond between 1 and 2, right? And a single bond between 2 and 3. Well, we can also draw the same structure, or very similar structure, but the double bond is going to be between 2 and 3 rather than 1 and 2. And if you calculate the formal charge for this, it would just be reflections of each other. So even the formal charges don't really tell us what the best structure is here. And that's where we need to use something called resonance structures. So an easy way to think about resonance structure is basically where there are multiple best structures. All right, so resonance structures are what we use when there are multiple best Lewis structures. All right, now, when we have resonance structures, basically what this tells us is that these electrons, you see the ones that make the double bond right here, right? They're going to travel back and forth between these two positions. So that's what happens. They move back and forth between these positions. And so it's very interesting because what's going to happen is you're not going to get a true double bond and a true single bond. Instead, you get something called a 1.5 bond. I know, we start going into half bonds now. But basically, when there's a resonance structure, the electrons move around so that there's not a real double bond and a real single bond. It's just somewhere in between. And so the way that we draw these 1.5 bonds is we're going to draw O3 like this. We're going to connect them with single bonds first. And then what we do is we draw a double bond, but we draw it dotted. And what the dotted line means is that the electrons are going back and forth between those positions. And so that's what we call a 1.5 bond. And this is what a resonance structure looks like.
Come up a lot.
Not often. Most of the time we'll get regular Lewis structures, but you need to be aware of them. Oftentimes you'll be asked to draw the resonance structures, and then you need to draw multiple. Yeah. Oh, yeah, we can still draw the lone pairs. I just chose not to. But the lone pairs will be... We usually omit it because the lone pairs start changing, because if, let's say the electrons are here more, you'll have the double if it's a double, and you'll have 3 on this side. So we usually don't draw the lone pairs for resonance. Great question, though. When do we draw the lone pairs? I'll be honest, you can omit them a lot of times unless they specifically ask for it. So even when you draw things like HF, oftentimes you're not going to have to draw the lone pair unless they specifically say draw them. Great questions, everybody. All right, so let's do one together. We're going to draw formate. Formate is HCO2 minus. So we're going to do this one together. Hydrogen has 1 valence. Carbon has 4 valence. Oxygen has 6 each, that's 12. And then the minus sign gives us 1 more. So we're going to add those up. So we're going to have a total of 18 valence electrons in formate. All right, now what I want you to do is, based on what we know already, I want you to try drawing formate. Don't think about resonance or anything like that. Just draw formate the way that you normally would, and then I'll talk about how you can draw other resonance structures from it. Okay, but try drawing formate. All right, everybody. So let's draw formate together, and then I'll talk about how we can get into the resonance structures. Okay. So we know that carbon is going to be in the middle, right? So we're going to attach everybody to carbon. So if we attach everyone to carbon, we have used 6 valence electrons. Okay, so we go from 6 to 12. Now, we need to get everybody to 8. So let's start with the oxygens. I'm going to give oxygens 6 each. That gets them complete. But if I do that, I run out of electrons, and what's our problem? Yeah, carbon needs 2 more, right? So the way that you draw formate, very simple. You just need to draw a double bond between a carbon and an oxygen. And you guys can kind of see where the resonance starts to come in, right? Now, don't forget to do the brackets and the minus sign for ions. So this is one resonance structure. The other resonance structure that we can draw is going to be the same thing, but this time instead of bonding with the carbon, the carbon and the oxygen going up, we're going to do one going to the bottom and to the right. Now, if you drew it differently, if you orient it a little differently, just switch the double bond to the other oxygen. That's going to be the resonance structure. So carbon, oxygen, oxygen, hydrogen. And then this time, instead of double bonding with the oxygen you had in this one, it's just going to double bond with the other one. All right, so those are the 2 resonance structures of carbon. Formate. Any questions on that? All right, so if we wanted to draw the dashed lines, the way that we would do it is the exact same thing. Just have the same orientation. Carbon, hydrogen, oxygen, oxygen. Hydrogen and carbon still have the single bond, but between the oxygen and the carbon, you'll have your dotted 1.5 bonds. Okay, and so this will represent, this pretty much is the combination of these 2 structures. All right, now before we finish up, let's talk real quick about bond length and whatnot. So we talked about this at the end of last class. We're going to end with this one as well. We talked about how single, double, and triple bonds, right? In terms of the distance, the triple bond is the shortest, right? Now, we have these 1.5 bonds. The 1.5 bonds, just like regular math, is going to go in between the single and the double bonds. All right, so if you have a 1.5 bond, the strength and the distance is going to be somewhere in between the single and the double.